In this unit, we'll be looking at gases, and will become very familiar with the ideal gas law, which is PV equals nRT, or PivNert. Looking on the periodic table, we see the elements that exist as gases, and they are color-coded on your periodic table. The ones that have a red outline, those are gases at 25 degrees Celsius and 1 atmosphere. One of the families is the noble gas family that's on the far right of your periodic table. And then we have nitrogen, oxygen, fluorine, and chlorine. And then don't forget hydrogen over here. Hydrogen is a gas and a nonmetal. It just hangs out with the alkali metal family because it has one valence electron. Here are some common substances that are found as gases at 1 atmospheric pressure and 25 degrees Celsius. These ones right here, they dissolve in water very easily, and when they dissolve, they form an acid. We have carbon monoxide and carbon dioxide. Here are those noble gases right here. And then we have oxygen, ozone, nitrogen. Nitrogen makes up about 80% of the air we breathe, and oxygen makes up about 20%, and argon makes about 1%. I know that doesn't add up to 100, but those are approximations. Let's look at properties of gases. First of all, gases, they have an indefinite volume and an indefinite shape. That means they take the shape of their container, and whatever volume you give them, they will expand to that. Now, they can be compressed into smaller volumes, and when this happens, the density is affected. They can expand without limits, and they completely and uniformly occupy that volume of any container, as I mentioned. They do diffuse into one another. Samples mix completely, and they do not separate out. So in the air that we breathe, for example, you don't have little pockets of nitrogen, little pockets of oxygen. It is completely mixed. It is a homogeneous mixture. It is also a gaseous solution, is another way to describe it. Kinetic molecular theory, or KMT, this says that all matter is composed of small particles that are constantly moving and colliding with perfect elasticity. And it just means that we have solid, liquid, and gas states of matter. And in a solid, the molecules are vibrating in place. In a liquid, they're slipping and sliding past each other and also vibrating. And in a gas, they travel in a straight line until they collide with either another gas particle or the sides of the container. When they collide with the sides of the container that they're in, they exert a pressure on the walls of that container. For gases, here's the kinetic molecular theory. And you should have a problem in your packet that is similar to this. But first of all, gases are in constant random motion. They have frequent collisions with each other, and again, that causes pressure. Each molecule of gas, it does take up part of the volume of the container that it's in, but we try to minimize that so our calculations aren't difficult. So we want to make sure that we keep the temperature high and the pressure low. And as long as we do that, then we can really just ignore the volume that the molecule itself is taking up in the container. When gas atoms or molecules, when they collide with each other, we assume that it's perfectly elastic. That means that in the collision, you are not losing any heat due to friction. When you look at the average kinetic energy of the molecules, it is proportional to the Kelvin temperature, and that's important in this unit. Whenever you're calculating and using temperature, you want to be in Kelvin temperature. That way you don't have negative temperatures. As the temperature goes up, the kinetic energy goes up, and vice versa. Now, individual molecules can have different speeds of motion, but if you look at the overall kinetic energy, if they're at the same temperature, they're going to be at the same kinetic energy. The pressure is caused by collisions of the molecules with the walls of the container, and there's a little formula right there that you'll never have to solve for, but pressure is force per unit area, and our molecules are very, 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 very tiny, and putting the unit area in the denominator like that and dividing it, you're going to get a pretty large pressure even though the molecule is so small. We assume that there are no attractive forces between the molecules and that each gas particle behaves independently. Number 7 is related very much to number 4. If two molecules have the same kinetic energy, that means they have the same temperature. So there's that relationship there. Just another look at pressure per force per unit area, and looking at that unit area, let's look at a ballerina dancer. So if she's standing flat-footed, like in that first picture, she's exerting a certain pressure on the surface of the earth. And I just did a little quick calculation so you could see mathematically what it could be. If she goes up on point, then that square area that she exerts, that number shrinks, and so you can see the pressure goes up. And then if she cuts that in half, so instead of being up on 2 toes, she's only up on 1 toe, you can see that the pressure doubles from before. So again, that unit area, that's an important calculation for this pressure, because again, we're talking about super small molecules hitting the size of their container. A man with the last name Torricelli, he was the first to measure the pressure of an atmosphere correctly. He noticed that water pumps could only take water up so high, and then they were not efficient. It didn't work anymore. He wondered what would happen if he filled a glass tube with some mercury. So he filled a glass tube with mercury and inverted it into a pool of mercury. And he insisted that the air molecules were exerting a pressure on the surface of that mercury, and also on and also it influenced the height of the mercury in the column. And then he was able to make measurements of what the atmospheric pressure was. So we use barometers today. Ours are more digital now, and in fact all the old mercury barometers they took out of the science department at the school because of the mercury. But what that barometer measures is atmospheric pressure. So when we have a storm come in, usually that means that a low pressure is over us, and so you see the barometer dropping, and then the storm comes in. On a nice clear day, the pressure is high, and so we have a sunny day. The standard atmospheric pressure is used to compare gases, and the standard unit of pressure is the Pascal. On your AP test, you will be given these first 3 calculations, and I would encourage you to find it on your data sheet. Also, you can memorize it so you can do your calculations faster. And I just put this down here so that you could compare to what you might see in your day-to-day life. So if you look at your automobile tire, it will say some sort of pressure and then PSI. That means pounds per square inch. So that is a pressure unit. In the lab, we use kilopascals. Pascal is a very, very small unit, and so a kilopascal is what we measure. What do our weather reporters use if we watch the news? They use inches of mercury. Now, if you were to measure somebody on Mount Everest versus somebody at sea level, you would see that the pressure is greater over the person at sea level. And that's because they have all those atmospheric molecules above them that are exerting a pressure down on the person at sea level. If you're up at Mount Everest, they often say that the air is thin up there, and it's true. And because it's thinner, then there's less collisions and then there's less pressure. So lower pressure up the top of a mountain. So backpackers know this very well. So they climb up top of the mountain and then they boil water to heat their food. And they find that it takes a longer time to cook their food at the top of a mountain versus back at home where they're at a lower elevation. Boiling is dependent on pressure. So when the pressure of the water that you're trying to boil reaches the pressure of the atmosphere, then that's called boiling. And at the top of a mountain, it will boil sooner, and so the water doesn't get as hot. And it's the heat that cooks your food, and so that's why it takes longer to cook something at the top of a mountain. And here's just another picture showing that there's more collisions closer to sea level, and up at the top of Mount Everest there will be less collisions. And again, if there's less collisions, then there's less pressure. So here's this column of air up through the atmosphere. You can watch a video on an ammonia fountain demo that shows the difference in pressure inside the glassware versus outside the glassware. And there's also a video that shows this tanker car crushing because of a difference in pressure. So that atmospheric pressure is bombarding us and our bodies every day. We just don't feel it because it's just a normal thing, but it is exerting a pressure on us. Pressure is affected by the force of collision. As the temperature goes up, those molecules really slam into their container. Also, the number of particles or the number of collisions that occur. So the more particles, the more collisions. So you would expect that this one would have a higher pressure and this one would have a lower pressure. And also the number of collisions. If I were to change the volume of my container here, I would see that the number of collisions is lower on here and higher here because there's just more of an opportunity to collide if the volume is less. Does the shape of the container influence the pressure of the gas? And the answer to that is no. As long as you're at the same temperature and the same volume of container, you're going to have the same pressure if you have the same number of molecules.